Welcome to the next video in abstract linear algebra. This is video 2 on lists. Oh, and I forgot to remark that this corresponds to chapter 1, section 1 of the textbook. So I'll do that now. So here we're talking about lists. Now, a list for us is just going to be any ordered finite collection of things. And so we're just going to start with pairs, right? So lists of length 2 is effectively what this is. And we'll go ahead and right away introduce the notation of the Cartesian product, the definition and the notation of the Cartesian product of any x and y, any two sets, x and y. The Cartesian product is the set of all pairs where the first coordinate of the pair comes from x, right? Because we're taking the Cartesian product of x and y. So the first one comes from x, the second one comes from y. So that's the Cartesian product between any two sets, x and y. Now we'll be particularly interested in taking the product of a set with itself, and the notation for that is x squared. And of course, if this works for 2, then we can extend this to any length n, right? So if you take the Cartesian product of x with itself n times for any natural number n, then that is written as x to the n. And if you have any list of, well, let's say that has n coordinates, then we call n the length of the list. For any given element of a list, if we write it as x sub j, so for instance, this is x sub 2, so that would be the case where j is equal to 2, right? This would be the case where j is equal to n. Well, what we call that subscript is the index of the element or its coordinate. Now, everything we've said so far does not require there to be any sense in which you can add or do, sort of algebra on the elements of the list. After all, the list elements, they could be anything. They could be sets. They could be computer programs. They could be just anything at all. But so starting now, we're going to assume that the elements are elements of a field. And because they're elements, the elements are from a field, then that means it makes sense to talk about adding the elements together and multiplying and so on. So we now have some two lists, x and y, from f to the n. And remember, f here is our notation for any field. It could be q, r, or c, although we're typically interested in r and c. But in any case, we have these two lists, x and y, and we're going to define what it means to add them together. Now, this is notation that I'm just going to, I know here I'm writing my lists horizontally, but it's really the same thing. And we often write things like this in linear algebra, right? We write our lists like that, making it a column vector, and we'll probably talk more about that later. But in any case, it's just totally equivalent, right? It's just a preference for how you either write it one way or the other, but it doesn't really make a difference, right? So if I write x1 to xn horizontally, it is exactly the same thing as writing x1 to xn in these square brackets, right? We kind of regard both of them as a list. Okay, we tend to think of this as maybe having more matrix structure, whereas this may not. But, whatever, it's not terribly important. So the fact that I slipped into my old habit of writing this vertically is not a big deal. They mean the same thing. So this is a column vector. I'm sure we'll talk more about such concepts later. But anyway, the important thing, right, what I really want to focus on with this equation is that if you have this list and it's got x1 through xn, and you have another list and it's y1 through yn, and we talk about adding the two lists together, how do we do that? What does it mean? For instance, suppose I have the list 2, 3, and I add it to the list 5, negative 2. Then we do it coordinate by coordinate. Exactly what you would expect, right? In fact, I guess I shouldn't belabor this point because I think we already said that a prerequisite of this is that you've already seen an earlier course in linear algebra. So of course, right, we're all familiar with this. Anyway, so there you have it. That's the definition of what it means when we add two lists of field elements, as long as they have the same dimension, which is to say length. So now that we have that definition of the sum of lists, we could use that to prove the commutativity of the plus operation on lists. That proof is given in the textbook, so I'm not going to bother giving it here. It's a pretty simple proof, so I think if you just see it in the book, you should be able to follow it without any struggle at all. Just as a matter of notation, and by the way, I'm going to always write my lists, that is to say my column vectors, with an arrow on top, just to emphasize and remind you and me that we're dealing with a vector, not a number, right? So when I have a 0 with an arrow on top, I mean the vector, that is to say the list of n zeros, where n is whatever, size of the space we've decided we're working in, right? Usually understood by context, right? So. Now, if x is any list in f to the n, we're going to define its negative. Its negative is any element such that when you add x and its negative, you get the 0 vector. It is very easy to show, and therefore I won't do it here. It is very easy to show that this negative always exists and is always given by basically this formula, this very, very simple formula. And finally, we define what it means to take a single field element, this lambda, and multiply our list by a single field element. Multiplication between lists of length n will not generally be defined, right? If you have two lists of length n, there is such a thing called the Hadamard product, but we won't really use that in this course. So for us, for the most part, something like vector x, vector y, right, multiplied together, that's going to be pretty much undefined for us. We're not really going to talk about multiplying two vectors or two lists together, but we will talk about taking a single field element lambda and multiplying that by some list. That is defined. And in particular, you just multiply every single coordinate.